Hello and welcome to this video about matrices. In this video we'll study Jordan canonical matrices. We'll make a computer function to test whether or not a matrix is in Jordan canonical form, and how to create random Jordan canonical matrices to test this function. Here are two examples in this slide of matrices in Jordan canonical form. There is firstly the zero region, that is, all of the elements in locations that aren't in the diagonal or superdiagonal. These should all be zero. Then there's the diagonal region that can contain any numbers, just like in a diagonal matrix. Then there's the superdiagonal region. It can contain zeros anywhere, but it can contain ones, but the condition for having a 1 is that all of the diagonal elements that are next to this one, either across from it or below it, must be equal. If it satisfies all of these requirements, then it is a Jordan canonical matrix, or a matrix that's in Jordan canonical form. The reason that this form of matrix is important is for finding functions of matrices like square roots and logarithms. Not every matrix is diagonalizable, but every matrix is convertible to Jordan canonical form. We can say that every matrix is Jordanizable. Now to write some code to test whether or not a matrix is in Jordan canonical form. We must check that the matrix is square and that only zeros are contained in the zero region. It is a bit different to the non-diagonal region in that it doesn't include the superdiagonal. We'll also set the return Boolean variable to be true and find an occasion for it to be false. We don't have to check the diagonal region because anything can be found there. Now to check the superdiagonal. This can only contain zeros and ones, and only ones when the adjacent diagonal entries are equal. We'll firstly make a loop to go through all of the diagonal elements, which doesn't include the first column. Then we'll calculate the row, which is the column number -1. Then we'll get the contents of each element in the superdiagonal. And if there is a number in the superdiagonal that isn't a 1 or a 0, like a 2 or 3, then we'll return false and exit the loop. In the case when we find a 1 in the superdiagonal, we'll check whether their adjacent diagonal elements are equal. If they aren't, then we'll set the return variable equal to false and exit the loop. And this is where we'll return the return variable saying whether or not this matrix is in Jordan canonical form. So now to make up random matrices to test this function in borderline cases, so as to make sure that this function is correct. We'll start with a Jordan matrix that has only 1, 1 in the superdiagonal. The two diagonal entries next to it must be equal to each other, like this matrix here. This function creates a Jordan canonical matrix with only 1, 1 in the superdiagonal. This first part resembles the function that creates a random diagonal matrix. Firstly, it sets every element to 0, and then it puts random numbers into the diagonal. So this part puts a 1 into the superdiagonal. Every possible location has an equal chance of being chosen. Then we'll set the two corresponding adjacent elements in the diagonal to be equal. We'll set the diagonal element that's furthest from the top to be equal to the one closer to the top. Now to create a function to create a Jordan matrix with a string of ones, that is, ones that are all next to each other in the superdiagonal. Their corresponding diagonal entries must all be equal. This is another function that creates a random Jordan canonical matrix. This time there'll be a string of ones. We'll calculate the length of the string here. We'll find a starting location for the string here, and this depends on the length of the string. And we'll get the value of the diagonal element at the start of this string of ones. We're going to set all of the corresponding diagonal elements equal to it later. We'll use a loop to write in the string of ones into the superdiagonal. Then we'll use a loop to write the same value into all of the locations in the diagonal, where they need to be equal. Now to make a Jordan matrix with two separate strings of ones in the superdiagonal. Each string of ones can have its own value in the diagonals corresponding to them. So now to make a random Jordan canonical matrix with two strings of ones, we'll start off by making a random diagonal matrix like before. Then we'll put the first string of ones in the top quarter of this matrix. We'll get half of the rows or columns of this matrix and put it into the variable n2. Then we'll get the length of the string and the location of the start of this string of ones and get the value of the diagonal element at the head of this string of ones like in the last matrix function. Then we'll copy this string of ones into the superdiagonal. And we'll make all of the diagonal elements that need to be equal here. Now we'll make a string for the second string of ones in the bottom right quarter of this matrix. Note that these strings of ones can merge into one string. We'll get the first diagonal element at the head of this string of ones. We'll copy this string of ones into the superdiagonal. And we'll make all of the required diagonal elements equal here. Now to make a non-Jordan canonical matrix that should fail the test. The two diagonal entries next to the 1 in the superdiagonal aren't equal to each other. Now to make this function that can create a matrix that's only just not in Jordan canonical form, we'll create a diagonal matrix with a 1 in the superdiagonal. Then we'll make the two diagonal elements that should be equal to be unequal to each other. We'll do this by setting one of them to be 1 plus the other. And we'll make a Jordan matrix with one of the diagonal elements wrong, because it isn't equal to the diagonal elements that it should be. I've circled it in green. Now we'll create this Jordan canonical matrix with a string of ones and one wrong diagonal element. We'll start off by making a diagonal matrix. Then we'll put a string of ones in the superdiagonal, with all of their corresponding diagonal elements equal. Then we'll make one of the diagonal elements wrong by incrementing it by 1. Now we'll create a non-Jordan matrix with a non-zero 1 element in the superdiagonal and coloured in green. Now we'll create this matrix that's nearly in Jordan canonical form, but that has a non-zero 1 value in the superdiagonal. We'll start off by making a diagonal matrix. Then we'll make a Jordan canonical matrix with a string of ones in the superdiagonal. Then we'll insert a non-zero 1 element into the superdiagonal, thus preventing it from being a Jordan canonical matrix. Now to create a non-Jordan matrix with a non-zero element in the 0 zone, so that it should fail the test straight away. This element is circled and coloured in green. Now we'll make up a function to do this. We'll firstly create a diagonal matrix here. We'll then make it into a Jordan canonical matrix with a string of ones and its corresponding diagonal elements being equal. We'll then get an array containing all of the locations in the 0 region and putting them into the array called list of locations. Then we'll get a random location from this list and set it equal to a non-zero element. Now to write a testing function that puts everything together. We'll make up these two loops. The first one does everything 100 times. The second one varies the size of the matrices we're testing from 4 rows to 11 rows. We'll create a Jordan canonical matrix. This one has only 1 1 in the superdiagonal, and then test it to see whether or not it is a Jordan canonical matrix. This function should always return true for this matrix. If it doesn't, we'll return an error, saying that it should have but didn't. We'll then test the other two Jordan matrix creating functions. And then we'll test the functions that create non-Jordan canonical matrices, but that could easily slip through the net and be seen to be Jordan canonical matrices by the testing functions. If all these tests pass, then the function is very probably working correctly. So I hope that you have found this video to be helpful and insightful. Please click like and subscribe if you did. Please leave some helpful thoughts in the comments, and thanks a lot for watching.